Thanks, Dick. Now let's go to the heat transfer process. John Kovat, tell us about how slagging, soot blowing, and other issues with heat transfer affect the formation of these pollutants in the boiler. Also, you might talk a little bit about other influences that come into play in the boiler that affect how difficult it is to separate these pollutants if we have to react to them downstream.
Sure, Steve. Historically, the Boiler Reliability Group has had little concern about environmental compliance issues. We've been so consumed with safety, reliability, and budget in the care and maintenance of the pressure parts that an attitude of "it's not my job" was a seemingly straightforward posture to take. It wasn't until the development of our alliance that our eyes here at UDC were open to all the aspects of plant operation, from the coal pile to the stack outlet. We soon discovered that in understanding the other processes that we would significantly improve our own specific scope of concern, the pressure parts. I can illustrate one example that exemplifies this fresh understanding of the entire process. Slag and the removal of slag of the heating surfaces, thinning ranks near the top of preventable tube leaks worldwide. We provide access, sandblast cleaning. We do extensive thickness readings utilizing ultrasonic instruments, then process massive amounts of data in the quest of eliminating boiler tube leaks. This is followed by tube replacement or repair to restore the original minimum wall thickness and adjustment and repair the soot-blowing devices themselves. What is typically left out of the equation is a joint effort involving the combustion performance and environmental people. As mentioned by Dick previously, if we get the combustion right, then the formation of slag and ash are reduced, and subsequently the removal of slag is reduced, and ultimately multiple benefits can be achieved. Our responsibility is to supply meaningful information in the form of quantity and specific locations of ash and slag to the combustion folks so they might better apply solutions to reduce the slag problem overall. This reduction of slag not only helps the overall tube life and reduction of forced outages caused by its removal, but also helps the distribution of heat more evenly across all pressure parts. Slagging causes plugging and poorly distributed heat transfer. Some tubes are much hotter than design, and some tubes are much cooler. Failures always occur at the extremes, not the average. This imbalance creates long-term overheat conditions in portions of a component. However, when we do a pressure part replacement of all the tubes is not normally necessary, but we do it because of the economies of scale. Many good tubes are scrapped and money's wasted due to premature replacement. Coal, fuel ash corrosion, for example, is temperature dependent for the corrosive chemical species to form. Plugging causes more unpredictability in location of this corrosion and makes managing the condition far more complex and therefore more expensive to control. The erosion, thinning rate of the tube increases to the square of velocity of the combustion gases. Slagging causes high velocity in some zones and low velocity in others. Therefore, high thinning in some locales and less thinning in others. When the boiler is not fouled due to slag and ash, it breathes more easier and more predictably. Certain locations of the original boiler design were intended to change the pressure drop and cause results of dropout of larger ash and slag to be removed prior to the boiler exiting. These would include the hopper bottom, the slag fence at the inlet to the back pass, a turn and dropout hopper at the economizer outlet. Flagging in many cases reduces the effectiveness of these design elements, causing high erosion rates, which concerns us, as well as higher ash loading of the air heater and environmental collection equipment.
Thank you, John. Dick, would you like to talk a little bit about air in leakage and the air heater, and how an innocent-sounding circumstance such as a little bit of air in leakage can influence MACT pollutants?
I'd be happy to, Steve. Famous last words, just a little bit of leakage. The average age of coal-fueled boilers in America is about 40 years old. As boilers age, joints, weld seams, boiler tube membranes, convection paths, tube penetrations, expansion joint cracks open up. The result is excess outside air gets it drawn into what we call the boiler setting. This is tramp air, or air in leakage. Air that leaks into a furnace bottom, ash hopper water seal, or through a penthouse or convection pass does nothing for combustion. But this air in leakage is sensed by the oxygen analyzers at the economizer exit, and it is treated by the controls as combustion air. The excess air that leaks into a suction-fired boiler is measured by an oxygen analyzer, just the same as air that was emitted through the wind box. This is an industry-wide problem, and it is very much underappreciated. Air in leakage can result in heat rate penalties on the magnitude of 300 BTUs per kilowatt hour. This can be quantified by oxygen rise measurements using a water-cooled HVT probe in the furnace, combined with air heater flue gas inlet and flue gas outlet traverses for traditional air heater leakage testing. Checking the oxygen rise from the furnace to the stack is useful. For a new boiler in operation and at normal excess air levels, the stack excess oxygen may be as low as 5%. Often, we test as much as 15% excess oxygen. This is a lot of air in leakage, and it is very costly from a fan power standpoint alone. It's even worse when the heat losses are calculated.
Dick, what about air in leakage at the air heater?
At the air heater, leakage is another factor. Regenerative Lungstrom air heaters should be capable of about 9% or better leakage rates. Leakage rates higher than 9% negatively affect boiler efficiency in two ways. First, with such high air in leakage rates, excessive auxiliary power for fans will be required to move the extra airflow. Second, the heat rejection of the flue gas is greater because wasted heat requires the operators to maintain the air heater's cold end temperature. Greater leakage rates mean more heat needs to be applied to the air entering to keep the cold end baskets above the acid dew point. When the boiler efficiency is calculated with a corrected to no leakage basis, flue gas exit temperature, the corrected temperature will be significantly higher when the dilution is accounted for. Just as an example, if the corrected to no leakage temperature is, say, 35 degrees Fahrenheit above normal or design, then this represents a full percentage point in efficiency penalty.
Interesting. Thank you, Dick. We've talked about where and how MACT pollutants are created and how we can control or influence process conditions. Jeremy, can you explain some specific effects that process improvements can have on emissions?
Sure, Steve. Dick and John have each discussed some important points related to improving the thermal efficiency of boilers, air heater performance, and air and leakage. Each of these factors can contribute significantly to the volume and temperature of the flue gas that's treated by the environmental equipment. Let's first discuss thermal efficiency, or unit heat rate. If we look at a case where the unit heat rate is reduced from 11,500 to 10,500 BTUs per kilowatt hour, the treated gas volume is reduced by 8.7%. If we correlate the effects of this thermal efficiency improvement to ESP performance, the result is a 26% reduction in outlet emissions. Now let's look at air leakage. In this case, reducing the stack O2 concentration from 7.5% down to 6% reduces the treated gas volume by 9.5%. This can produce a 22% reduction in outlet emissions. Finally, let's take flue gas temperature into account. If we look at a case where the flue gas temperature is reduced from, say, 350 degrees down to 280 degrees Fahrenheit, the gas volume is reduced by about 8.6%. In this case, since flue gas temperature is also critical to ash resistivity, ESP performance is improved through two methods. The result is that the outlet emissions are reduced by over 36%. It is also important to note that any reduction in gas volume should also reduce the quantity of any sorbent feed rates that are needed.
Thank you, Jeremy. Now we've talked about where and how MACT pollutants are created and how we can control or influence that. Now let's move downstream. Jeremy, on the back end of the plant, what are some effective ways of reacting to particulate matter, mercury, dioxin and furan, CO, and HCl to prevent these pollutants from exiting the stack?
Well, Steve, I thought it would be helpful to show a case study that illustrates what can happen on the back end, what we can do to respond to all the factors we've been talking about here this morning. This chart displays the current particulate emissions and various improvement options for each of the boilers that we discussed earlier. We use our experience with various equipment designs and process characteristics to suggest cost-effective improvements. We then use our precipitator performance model to predict the future emissions levels that would be achieved with each option. Some of the options are strictly related to process conditions. For example, we know that dioxin and furan levels reduce dramatically if the precipitator inlet temperatures are reduced below 350 degrees Fahrenheit. This process change will also reduce particulate emissions by reducing treated gas volume and ash resistivity. In this case, we predict that this process change would bring all of the boilers into compliance on particulate except boiler number 8. Many other possibilities for improving precipitator collection efficiency. These include optimizing power supplies, making flow distribution improvements, and upgrading internal components. With this modeling process, we can predict which combination of options produces the best value. Once we are in compliance with the particulate emissions, we recommend reassessing the MACT pollutant emissions. If mercury and hydrochloric acid are still an issue, it's probably time to start evaluating various sorbent injection systems.